because it's very easy to get you excited about the session. All right, so this is about computation that's happening outside the computer. Okay, so the first paper is about computation inside the brain. Okay, so there the computing units are neurons. The second is about computation inside your genes. Okay, so there the computing units are like genes and cells. Okay, the third talk is about things like social learning. So how do, for example, like things like language acquisition happens, and in more general, things like social norm transmission. And the last talk is about computation that happens, let's say, inside your kitchen. So how does like mold actually compute anything with you? So that's already pretty exciting. And I want to like continue to like get you pumped up by giving you these 4 different sort of like mental images. Okay, that more or less like incentivizing each of the talks. Okay, so for example, like think what's going on in your brain right now. Okay, so you're receiving several different like stimuli. So maybe like light coming from the fixtures above, or you see like slight movement outside from the trees, or you hear some sort of like ambient noise from the air conditioning, and you also like hear my voice. And somehow, hopefully, you focus on my voice. So this seems trivial, but actually it's a very, very hard problem to do in a decentralized way using spiking neurons. Okay? So you have like many inputs, you have like many outputs, and somehow you have to like activate a single of these outputs and something that like corresponds to a meaningful input. Let's say the most important input. Okay? So this is a very famous problem of computational neuroscience that's known as the winner-take-all problem. Okay? And in the first paper, Nancy Lynch, Cameron Musco, and Meirav Parter, they studied this problem from the perspective of computer science, theoretical computer science, and specifically capturing things like trade-offs. Okay? So for example, like upper and lower bounds on the convergence time, and how does this like compare, like depend on things like probability of failure and number of hidden nodes. Okay? And they also identified some very interesting connections to like the use of randomness. Okay? When is randomness, for example, beneficial, and when it's like not for this kind of like computation. All right? So second mental image. Okay? It's about mutation and survival. All right? So you might have seen some sort of like small moths, like wherever you live. So moths are like really slow creatures, okay? And they're being preyed upon by very fast predators. So the way they survive is like they try to blend in, okay? So if you have like white somehow like barks in the trees in your neighborhood, your moths are most likely going to be white, okay? But sometimes weird things happen. For example, like maybe there's pollution, maybe the trees in your neighborhood sort of like gets attacked by some sort of like moss, and the change of the bark actually, the color of the bark actually changes. And it turns from white to, let's say, gray, okay? Now, within like a few sort of like months, something amazing will happen. So moths in your neighborhood will turn from white to gray, okay? Why is that the case? Well, the white moths now are like easy prey to like fast sort of like birds, okay? And luckily, like a mutation will happen, and maybe like a new sort of like moth will turn like gray just by accident, okay? And what we'll show in this paper will actually develop models that are like robust and fast that actually give a formal explanation of how such a process can happen, okay? And this is joint work with Ruta Mehta, Ioannis Panagias, Prasad Etali, and Vijay Vazirani, okay? Now the third paper is something like really exciting again. And here's like a different mental image that's also like a cool party trick, okay? So go in a party and find one random victim and ask you here, like, okay, give me like a sketch of an owl, okay? So you does his best thing, his best for like sketch, and then passes on to Bobby. Bobby is not told that this is an owl, he just sees the sketch, he tries to produce a copy of the sketch, and so on and so forth. So now Bobby passes on to Christos, and so on and so forth. And after like 7 or 8 iterations, we all look at like what's the final like image. And typically, in a normal party, the image will be a cat. Right? So what has happened like is the system has actually equilibrated, but in a very bad way. So by this process somehow like reaching fixation, the initial stimuli has died. So you don't learn anything about what was put in the system, okay? What you see is some sort of like common prior about like, what rocks average people vote, okay? People like see cats, they like cats, eventually they see cat when you see like a scribble. Actually, I'd be very, very curious what happened if you run the experiment here. Some sort of like weird graph theoretic like object at the end, all right? So Bernard Chazelle and Chu Wang argue what happens in order for this sort of like process to not kill somehow this initial information, which, for example, like necessary for things like language acquisition, where one generation teaches a language to the following generation, is somehow that the learning from like epochs must slowly increase. This effectively leads to some sort of like inhomogeneous, like Markov chains that actually never fixates. And this is a very cool example where actually non-equilibration is actually necessary for a very sort of like meaningful computational process to be, useful, right? And finally, like last but definitely not least, like I think like one of my personal favorite papers, and arguably maybe one of the best papers from my perspective in the conference, is this very cool paper by Damian Strazak and Nishi Vishnoi about an equivalence between like two completely different dynamical systems, okay? Okay, on the one hand, we have like a kind of mold, like a really smart mold that is able to do solve really hard computational problems, okay? So my last mental image is the following, okay? Imagine like a really weird maze, and you put cornflakes on one entrance of the maze, and you put cornflakes also at the exit of the maze, and you develop like a small mold community on the entrance, okay? So what mold will actually do, it will start like spreading around, eating this initial somehow like pot of like cornflakes, and spreads itself throughout the network. And when it actually finds the actual end, like it contracts itself, and out of all possible paths, the only path that survives is the shortest path, okay? This is truly an amazing phenomenon, okay? An amazing phenomenon. And Nishi Vishnoi has been like very seminal with his work in terms of explaining how these dynamics actually work, okay? But what makes this paper really amazing is that there's a connection in the opposite direction, okay? This paper does not try to, let's say, interpret how a biological process works, but actually uses biological process and like mathematical tools developed to it to argue something about the convergence of one of the basic tools in, let's say, in compressed sensing and sparse recovery, okay? So now we have like a proof that for a specific class of iterated reweighted least squares, they actually provably converge, okay? And I want to end by saying that like molds are very generous creatures, okay? So you give mold, let's say, a very, very sort of like mediocre cheese, it gives you like amazing cheese, right? Mold, you come up with a cold, you go to the doctor like, develops some mold, gives you penicillin, now you're healthy again. So Strazak and Vishnoi, now they tell you, okay, suppose you have like a really hard headache induced by a very hard theoretical problem, okay? You can actually find another solution, a cure to this headache, just by using like a mold-inspired cure, okay? So I hope you're excited about the talks, and I definitely am. So let's start.